Welcome back to PV Online. Today we're going to look at inclines, and in particular, what happens to the acceleration of an object on an incline. All right, I'm not a very good artist, so very often I will use blocks, but keep in mind this could be anything. This could be a sled going down a hill. This could be a car rolling down a hill. All right, so anything that's on an incline, we're going to follow this same procedure. All right, so in this case, we have a 5 kilogram block. It's accelerating down an incline. And the first thing we want to do is draw a force diagram. Now this force diagram is hugely important. First things first, we know all objects on Earth are going to have a weight. So we're going to have mg. That's going to be the first one that we have. Now the second force that we know is going to be the normal. And now remember, the normal is perpendicular to the surface. So in this case, my normal is going to be going up and to the right. So the normal force is going to always be perpendicular to the surface, so it's going up and to the right. And in this case, we have friction. And remember, friction opposes motion. So friction is going to be going up the incline. All right. So we've got those three forces acting on our block. So let me go ahead and write in friction here. We know that the block is going to accelerate down the incline. It's going to accelerate down the incline like so. So any force that is parallel with the acceleration or perpendicular to it is perfectly fine. Which one is not? You'll see that friction is parallel in the same plane as the acceleration. The normal is perpendicular to it, but our problem is going to be mg. And mg goes down the incline and into the incline. And what we have to do is we have to break it into its components. And what we're going to do with this one is going to happen every time you have an incline. So the first thing I want to do is I'm going to find out how much of this goes into the incline, like so. And the second one is going to be how much it goes down the incline. Now remember, this is vector addition, so where one ends is where I'm starting the next one. And you can see that I've made this beautiful right triangle because I've broken up mg into these two components. We're going to call this the vertical component and the one going down the incline the horizontal component. Now the thing that's interesting about this is that this triangle right here and this one, they are similar triangles. And that means that this angle up here is going to be 50 degrees. It is always going to match whatever is down at this bottom part of the incline. So the 50 degrees will match here, which means that this component that's going into the incline like so is going to be the adjacent one, which is going to make it mg cosine of theta. This component is going opposite, or it's opposite of the angle. It's going down the incline. Opposite is going to be sine, so this part will be mg sine of theta. Now every time you have an incline problem, you're going to have to break up mg into these two components. So let's go ahead and take a look at this example. So we have this 5 kilogram block. It's accelerating down an incline. We drew the force diagram. We have a grand total of 3 forces acting on the block, but I had to break up mg into 2 other ones. It says find the acceleration of the block if the friction or if the surface is frictionless. Ah, darn it. So we want to, let's not include this friction. So let's draw that over here. I'm going to come over here to this one. And so again, we have mg acts straight down, and we're going to have the normal. Again, it is perpendicular to the surface, so it's going to go up like so. So we've got the mg here. We have the normal. This is going to be the for answer for part A. This will be for part B. Again, the block is going to accelerate down the incline, and you'll notice that I'm not putting the acceleration on my force diagram in the sense of at this point, because acceleration isn't a force. It is the result of a net force, but it's not a force. The normal is perfectly fine because it's perpendicular to the acceleration, but mg is a problem. So once again, we need to break mg up into its components. And make sure you look at this. Do you see how the mg, I've got the component that goes perpendicular to the surface. And I very purposely ended it right there so that I could make a nice right triangle. We've got the angle right here is going to be my 50. So we've got mg cosine of theta, and I'm going to have mg sine of theta. All right, so for part A, it asks you to find the acceleration of the block. So I'm going to start, as I always do, with the sum of the forces equals the mass times the acceleration. Now in this case for part A, which force is going down the incline? Which force is causing that acceleration down the incline? And we know it is this force. Now it's not mg, but it is mg sine of theta. And that's going to equal ma. Now there may be times where you're not given the mass of the block, and in this case that's all right, because look at what happens with the m's. They cancel out. Now they're only going to cancel out if there's an m in each term, but this is an example when it does. So if I take 9.8 times the sine of 50, that's going to be my acceleration. My acceleration then is 7.51 meters per second squared. So for part B, let's go ahead and add in friction. So we're going to add that third force. So now with B, I've got the sum of the forces equals the mass times the acceleration. All right, a handy idea would be, let's take a look at all of the forces that are acting parallel with the acceleration. Now remember, the acceleration is going down the incline, and we know that mg sine theta is pulling down the incline. But do you see any other force that is parallel with the acceleration? And it would be friction. Now my arrows aren't really the appropriate size, because since I know it's going to be accelerating down the incline, that mg sine theta should have been larger, should have been longer. I want to make the force that's in the direction of the acceleration positive, so I'm going to make that mg sine, of theta minus friction. And why is it minus friction? We know it's accelerating down, so mg sine theta, gravity is pulling you down the hill. But friction's opposing it, so that's why it's minus friction equals mass times acceleration. So we've got to figure out what friction is. Now remember, by definition, friction equals mu times the normal. So now I've got to figure out what that normal force is. So instead of looking parallel with the acceleration, I'm now going to look at what's going on this direction. So I'm looking at these two forces. And I know that the normal is going to be equal and opposite to mg cosine theta. So I could come in here and just say friction equals mu times mg cosine theta. Mg cosine theta is simply how much the incline has to push up to hold the block up. So if we substitute in where I had friction, minus mu mg cosine theta, that equals ma. Now once again, if you weren't given the mass of the object, it wouldn't matter, because I could cancel this out. So I'm going to take 9.8 times the sine of 50 minus the coefficient, which is 0.15, times 9.8 cosine of 50, and that's going to be my acceleration. So our acceleration now is 6.56 meters per second squared. And does that make sense? Look, before, when I had no friction, my acceleration was 7.5. Now all of a sudden my acceleration is smaller, and that's because friction's opposing our motion. Now keep in mind what happens here, the steeper the incline, the more of gravity is pulling you down the incline. The largest your acceleration could be would be 9.8, because then you would be in free fall. Then you would actually have a vertical incline. All right, let's start with a force diagram, and I'm just going to use a dot to represent my crate. And we know that we have gravity, and gravity is going to be acting straight down. So I'm going to put that force down like so. Whoops. And we know the incline is going to be pushing up. We call that the normal force. This time I have an applied force going up the incline like so. This is how much we're pulling up on the incline, or up on the block. So now, since this block is going to be moving at a constant velocity, and I'm going to say it's going up the incline, that means friction opposes motion. We're going to say friction goes down like so. All right, so let's go ahead and fill those in. So we know we have mg, we have our frictional force, we have the normal, and we have our applied force. So let's say that it's moving up the incline with a constant velocity. Now this would be something you'd have to be told, so that would have to be embedded in the question. But let's say that we're moving at a constant velocity up the incline. All right, do you see that the applied force and friction, they're fine. They're parallel with the motion. The normal's fine because it's perpendicular. Which one of these four forces is the problem? And that would be mg. And so in order to fix this, we're going to have to break mg into its components, into its vertical component here, which is what we're going to call this one going into the incline, and the horizontal, which is going down the incline. So now remember that our angle of the incline is going to equal that angle. So this is going to be mg cosine of theta, and the one going down the incline is going to be mg sine of theta. Whoops. We're ready to start, so I'm going to start, as I always do, with the sum of the forces equals the mass times the acceleration. This phrase is huge, and that's because if you're moving at a constant velocity, that means your acceleration is 0. So I'm going to make, because I want to, I'm going to make the applied force positive. So I have the applied force is going up the incline. Friction is opposing it, so I'm going to make that minus friction, minus mg sine of theta. And I know that those forces all sum up to equal 0. I'm only focusing on the forces that are parallel with one another when I come up with this statement. I'm going to do it again in a moment when I start looking vertically, and I'm going to be looking at these two, the normal and mg cosine of theta. And we know that they'll be equal to each other. Now, the reason that's going to be important is because I need the normal when I do friction. The sum of the forces acting vertically, they're going to also equal 0. That means the normal is going to equal mg cosine of theta. So I'm looking for the applied force, that's what we're looking for, minus friction, and friction equals mu times the normal, minus mg sine of theta. That all sums up to equal 0. So in doing our applied force, minus the coefficient of friction, which was 0.12, the normal is going to equal mg cosine of theta. Now this time I am not able to cancel out the m's. And the reason I'm not able to cancel out the m's is because there's no m in the applied force. So this is going to be times 9.8 cosine of 30 minus the mass of this thing, which is 100, times 9.8 sine of 30. Those all equal 0. I'm now able to solve for the applied force. And I get a total of 592 newtons. I'm going to do another example. If you feel like, oh, I know what I'm doing, feel free to start the homework. If not, go ahead and just take a look at another one and see if you can do it on your own before I do it. Okay, our last example says determine the acceleration of a 60-kilogram skier going down a 22-degree hill with a coefficient of kinetic friction of 0.13. Kinetic just simply means because it's moving. So I'm going to start with my dot for my skier. And I know I have mg acting down. I have the normal going up and to the right. And now which way is friction going to be acting on our skier? And it's going to be acting up the hill like so. And she's going to be accelerating down the hill. So the normal is perpendicular to it, it's fine. Friction is parallel, it's fine. mg is a problem, we have to break it up. Have you noticed we're doing this every single time? mg sine of theta, and mg cosine theta. We're doing this every single time we have an incline. Sum of the forces equals the mass times acceleration. Which force is causing the skier to go down the incline? We know it's gravity, but it's not all of gravity. It's not mg. If it was mg, she would be in free fall. She's not in free fall, so it's just mg sine of theta. Friction's opposing the motion, so we're subtracting it, equals the mass times acceleration. Mg sine of theta. What does friction equal? And we know that friction equals mu times the normal. And in this case, the normal equals mg cosine theta. So I'm going to come over here and go mu times mg cosine of theta equals ma. Look what happens this time with the m's. They all cancel out. I have 9.8 sine of 22 minus 0.13 times 9.8 cosine of 22 equals A. I forgot the 2 there. All right, let's solve for the acceleration. And I get 2.49 meters per second squared. It's a lot less because our angle is a lot flatter. It's only 22 degrees, whereas before I think we were at 50. So now we're much closer, or much more of that force then is going to go into the incline than pulling you down the incline. All right, you've seen several examples on what to do on an incline. We'll see you next time.